All right, chemists, let's get started. We're going to do chapter 16 for a little bit. I just want to get to pH. I hope it won't, I don't think it'll take more than half the time. And then we'll do the rest of the class for midterm 1 review. So I'll just work through the remainder of the Zoom packet. I hope you know where to find that. It's like on the Zoom review page. There's a packet with a key. I'm so sorry I did not record it. I was kicking myself. I literally, really, like, you saw my face. If you were there yesterday, you saw my face when I realized, like, literally the last minute we were there, that I forgot to record. So I don't know if you guys audibly gasped at home, but yeah, I'm so sorry I forgot to record. It's a little button that I forgot to press at the beginning. I haven't taught in a long time, or like a couple months, so I forgot how to teach on Zoom. Yeah, so I'm really sorry that I forgot to record it, so I'll try to make up with it by doing some more review today. But everyone has the key, okay? And my keys are pretty detailed. I try to include every little bit of information there for you to get to that answer on your own. You don't need me yelling the same things to your face when you have that key right there. All right, so I think chapter 16 will help you for the exam too, because the whole idea here is we're looking at a different kind of equilibria, acid-base equilibria. So it's still equilibria. It's still K. It just so happens to be with acids and bases. So this will help us a little bit for chapter 15. The idea that, okay, we still have, equilibrium arrows involved. We have a forward reaction, a reverse reaction. We're just relating it to acids and bases instead. Instead of our full reaction arrows that we learn in Gen Chem 1, where those are irreversible processes. All right, so this is what we're going to talk about today. I hope to get to maybe here, I don't know. Okay, so acids and bases. We think about neutralization reactions, titrations, right, with acids and bases. So historically, how they categorized acids and bases gives rise to a bunch of different theories that we currently use today. So we'll look at three different types of theories to categorize acids and bases. So historically, when they identified acids, they tasted sour. Bases were identified as bitter. Obviously never taste chemicals in lab, but looking at the substances that we interact with in our everyday life, some of them are acids, some of them are bases. All right, and it all has to do with the composition that they have. So these are the three categories that we will study in the next coming slides. This is basically a summary of what these different theories look at. All right, because in Gen Chem 1, when I said acid, you think of something like HCl, something that donates a proton, H+, right? You think of that. When I say base, you think of sodium hydroxide, donates a hydroxide. That's basically the Arrhenius definition. Then from there, we can expand and make our definitions more general so we can apply it to more things. But the beauty is that all these subsequent theories still apply to the whole H plus OH minus gives you water idea. So yeah, so let's just go into it. All right, so acids and bases. All right, so the Arrhenius acids and bases, this is the first kind of theory that came about, and it's the most similar to how we learned it in General Chemistry 1, where we have H plus OH minus gives us water. That's our neutralization reaction. So basically, an Arrhenius acid says that when you dissolve a substance that's an acid, it increases the H plus concentration. So what you're looking for is a substance that has H plus in it. So we could have something like HCl. That's a strong acid, so not an equilibrium, but we learned about it, right? Or a weak acid like HF. Do you remember the 7 strong acids? Let's just do that right now. The 7 strong acids. Do you remember them? So I remember the halogens, HCl, HBr, HI, but HF is not included. HF is actually a weak acid. All right, and then I do my polyatomics. HNO3 nitric acid is strong. H2SO4 is strong. What's the next one? HClO3, so chloric acid, and HClO4, perchloric acid, are both strong acids. All right, those are our 7 strong. Those are in the textbook. Okay. What's nice is if you know the 7 strong, that means all other acids are weak. And that's how I know HF is a weak acid. All right. All right. And how else do we know from these formula, or these balanced chemical equations, how do we know HF is a weak acid other than me saying it? HF is a weak acid because what's different in those balanced formulas or balanced equations? Yeah, it's reversible. HF has that double arrow that indicates it's at equilibrium. All right. Because weak acids do have chemical equilibria, strong acids do not. Yeah, because let's think about it, kind of on the terms of K, right? If we wrote the K expressions for both of these, we would put H plus times F minus over HF, wouldn't we? For HCl, we would put H plus times Cl minus concentration over HCl, wouldn't we? Okay, yeah. HF, we're saying, hey, we have this equilibrium arrow. Both sides of this equation exist at the same time. We can put those concentrations in for K. What about HCl? When HCl dissolves or, dissociates in water, what side of the arrow here dominates for HCl when HCl dissolves in water? Remember, it's a strong acid. It's a strong electrolyte. So does HCl neutral exist in water? No, it only exists as H plus and Cl minus. So the only substances present are where? On the reactant side or product side? Product side. So we have a big number on our numerator for the K expression for HCl. So a really big number on the numerator, but what's the number on the bottom? 0. Is there any HCl neutral in a strong acid solution of HCl? No, there's not. It's a strong acid. All of it dissociates. So do you see how HCl does not have a K associated with it? Do you see that? Because it's a strong acid, it's not a chemical equilibria. And it's because K is infinitely large, essentially, for that process. Okay, sorry, I digress. All right, those are acids. It essentially just says, hey, it has H plus. Bases, on the other hand, are just saying, hey, it's a substance that when you add it to water, it increases the OH concentration. So I have 2 examples here. Right? I mean, you don't have to write them down, but the 2 examples, something obvious like sodium hydroxide is a base, because you add it to water, there is a hydroxide anion. But something that's a little less obvious is ammonia. Do you remember in 1210 when we asked you to memorize the weak bases, we only asked you to memorize 1? Do you remember that? And which one was that? It was ammonia. We will learn in this chapter, there's way more weak bases, but here I show ammonia behaving like a weak base. It's a weak base because when you add this to water, NH3 to water, it grabs one of the hydrogens off of water and it steals one of those hydrogens, so you get NH4 plus or ammonium and OH minus. So do you see how we produced in this the second green reaction, we produced OH minus a different way. It's a little bit different, but we still made OH minus, as a product, so we can call it or categorize it as an Arrhenius base. In this case, it's just a different way. Anyway, so these ideas, these categories, Arrhenius acid, Arrhenius base, were all based upon observations. What Arrhenius observed is when he mixed an acid with zinc, bubbles formed. Oh, I just had this demo for 1210. I should have kept it. So if a substance if you have a substance and it's acidic and it makes bubbles with zinc metal, what that is saying, hey, there's H plus present, that substance is an acid. So all of these categories were based upon observations. When you if you had something, all right, you had a liquid of something, you didn't know if it was acidic or basic, You tasted it and it didn't taste like anything. I don't know. Don't taste any chemicals. But the observation is if you poured an unknown substance on zinc and it bubbled, that is an acid. Because if we remember in solution chemistry, when we talked about the activity series, do you remember that? Do you remember the activity series? I just taught it today. All right, the activity series. In order for a redox reaction to go, the metal, the solid neutral metal needs to be higher than the cation. So H+, that's acid. So we're basically saying if, hey, we put acid in contact with zinc and it bubbles, there's H+ present to make those bubbles. The bubbles are H2 gas. So that's how observationally he discovered or categorized acids. He took a bunch of unknown substances, mixed them with zinc solid. If it made bubbles, it was an acid. On the other hand, if it didn't make an acid and instead it made a solid when mixed with magnesium 2+, he called it a base. And that the reasoning is because magnesium hydroxide is insoluble in water. So if there's hydroxides around in an unknown solution, it's a base. If you mix magnesium 2+ with it and you make a solid, that tells you that there's hydroxide present. So that's how he came up with this definition, just based upon observations. Think about you have these unknown, clear, colorless solutions and you have no idea what they are. So you start throwing zinc or magnesium 2+ in it to identify, hey, is it an acid or a base? All right, so it's just based upon observations. The idea H+ indicates something's an acid, OH- indicates it's a base. Let's go into a more sophisticated definition of acids and bases, and that's the Bronsted-Lowry acid-base definition. So instead of thinking about H+ as being an acid, we think about H+ as being a proton. All right, so now we're thinking about proton transfers within reactions and within structure. So recognize Bronsted-Lowry acids and bases, they call H+ a proton because H+ cation is a proton. Right? Hydrogen has a mass number of 1 and it has one proton, but to be neutral, it also has 1 electron. So if we remove an electron to make a H+ cation, literally the only subatomic particle present there is just a proton when it's H+. There's no electrons or anything, right? So that's why we can call H+ a proton. So this is more sophisticated, this definition, because we actually need to know a little bit about the structure and the chemical formula involved in this chemical reaction to see where protons are moving during a chemical process, during a chemical reaction. So here, Bronsted-Lowry acids, you just have to memorize this, is a compound where a proton can be removed. Again, proton just means H+. So a substance that can remove a proton or donate a proton is an acid. A substance that can accept a proton is a base. So if we think about this in terms of acids and bases, we already know. Okay, here's the big idea. We need to know where is that H+ going. So here I'm showing you, hey, we have a strong acid, nitric acid. Okay, it's a strong acid, so we know that all of those H+ are going to dissociate from those nitrates. So if we track what's happening in this reaction, we see that this hydrogen, right here, this hydrogen is going to get donated and accepted by the neighboring water molecule. Because if you see on this other picture here, do you see where that proton went, where that white ball, that hydrogen went? It went from the nitric acid to the water molecule. So do you see that? So if we go back to our definition, nitric acid, did it accept in this reaction, did it donate a proton or did it accept a proton? It's donating. On the other hand, water, is water donating a proton or is it accepting a proton here? It's accepting. So you see that our acid source, HNO3, this is our proton donor. So that makes it an acid. Water here is our proton acceptor. All right. And then that's where our H+ went. right there on water. So we've been lying to you all this time, okay? When we say that HCl is a strong acid, it dissociates into H plus and Cl minus. I lied to you. H plus doesn't actually exist, okay, in water. In water, it doesn't exist. H plus is always attached to a water molecule, always. So more appropriately, we should be calling H plus H3O plus. It's always attached to a water molecule, all right, H3O plus. But you see, chemists are lazy, and it's easier to just write H plus in you know, when doing lots of math or whatever. But do recognize that H plus, you won't see just small little H plus cations floating around. They will always be attached to a water, like piggybacking on a water. Does that make sense? But chemists are lazy that we don't want to write a 3, an extra 3 and an O. Okay, so we'll just write H plus instead to mean the same thing. So H3O plus is called hydronium, and it's just the cation form where we have that H plus, that acidic proton attached to a water. Okay. So this is kind of wrong when I write this. It really should be plus a water molecule. You get H3O plus, Cl minus. But again, chemists are lazy, and we don't like to write that. It's too much work. All right. Yeah, and so the big idea here with our Bronsted-Lowry definition is we need to kind of know the formula, the structures, and see where that proton is going. Remember, just proton means hydrogen. Okay, let's do the last one. Okay, this is Lewis acids and bases. So instead of thinking about protons, we're looking at movement of electrons. So again, you need to know the chemical formula, the structures to kind of understand this. So think about an acid, a H plus proton, right, that we talked about in Bronsted-Lowry. A proton has no electrons, okay? It lacks electrons. So that's why we call Lewis acids and bases, or sorry, Lewis acids electron acceptors. Hydrogen has no electrons, it only has a proton. So typically H plus will accept electrons, that it's going to take electrons from somewhere else to form a new bond. Versus Lewis bases are electron donors to form a chemical bond. So this is the difference. But again, with all of these definitions, they build on one another. So all like Bronsted-Lowry and Lewis acids, those two acids, they're both acids. All the bases, they're both bases. It's just different ways to think about it. So let's look at this. Let's look at a general generic acid-base neutralization. So we combine H plus and OH minus, we get water, right? HOH. If we think about that, like how the bond is being formed, see how like we kind of make a new bond right there? All right, it's like a joke I tell in 1210. I'm like, H plus OH is HOH. What is that? And then usually clever people, they say, oh, that's water, H2O, you know. But the thing is, when we write H2O, it ignores what bond is being formed. We're making a new bond between that hydrogen and that oxygen. That bond contains what? A bond is made of 2 electrons, right? All those bonds are made up of 2 electrons. So again, this is why in our Lewis acid-base definition, knowing where electrons go is really important. Because in order to form this bond, do you see how the electrons have to move? Hydrogen has no electrons to give or to donate. So instead, it's going to accept those electrons from that OH molecule, or that OH anion. So it's really important to recognize like Lewis structures here, okay? Because I can write OH minus, but if you write out the whole Lewis structure for OH minus, you would see that there are 3 lone pairs around that oxygen in order for it to have a complete octet within there. Right, so do you see how that bond's being formed? And so the new thing we make is H, there's the new bond, OH, that's water. And do you see, look, do you see the water and how it has how many lone pairs on it? 2 of them. And then obviously there's a bond right there too. I just kind of drew it in a way to show how this chemical reaction is going. So which is our Lewis acid? What substance is, what's a Lewis acid? Accepting electrons. H plus is our Lewis acid. And then that would make OH our Lewis base because it's donating the electrons. But do you see how it's still consistent with H plus is an acid, OH is a base? You see that? Still consistent with it. It's just instead of thinking about protons, we're thinking about electrons. So the definition still fits that. So, you know, in that obvious case where we have like H plus, an acid, OH, a base. Let's look at an example where it's not so obvious, where what's the acid and what's, oh, I already have the answer, but whatever. Okay, so here we have a substance. We have NH3 combining with BF3 to give this compound. So see how the bond is being formed. You kind of have to look at both sides here, right? The new bond that is formed is right there. And so drawing and understanding where the electrons are going, what substance is donating the electrons? The nitrogen. Do you see how the nitrogen has electrons and it's giving it to that boron? And then boron is accepting the electrons. And so that's how we give rise to, you know, identifying what is a Lewis acid, what's a Lewis base. And so the answers are right there. Okay, base is the donor, acid is the acceptor. If you ever forget Lewis acids and Lewis bases, just write H plus OH minus and remind yourself how we make water, right? And you see that. And I say, oh, okay, OH has to be a base and it's donating the electron. So if you forget, just kind of fall back on things that you already know. Good? All right. There we go. Okay, so those are Lewis acids and bases. We will mainly worry about these last two. These two. Okay, so I already mentioned that this chapter is about chemical equilibria. It's just about acids and bases, so we're doing these double arrow things. So the idea here is when we put weak acids or weak bases in water, they make these chemical equilibria with water itself. Water can either donate a proton or accept a proton. So we have to come up with some definitions here that we need to use. So we know NH3 is a base, right? It's a weak base. But when you put it in water, it grabs a H plus, an H plus to make NH4 plus. So how all of these things are related is when you have a weak base, right, like this, NH3, and it gains a proton, you now make a weak acid. So NH4 plus is a weak acid when we have a weak base gain an H plus. So that's what this conjugate acid is when we take a base, we add a proton, you get a conjugate acid. It's the complementary base forms, I think I have these backwards. When a Lewis acid, do I have these backwards? Hold on. The complementary base formed when a Lewis acid, yeah, sorry, these definitions are backwards. Complementary acid formed when a Bronsted base accepts a proton. Well, conjugate base is you start with an acid, it loses a H plus or it donates an H plus, and now you are looking at your conjugate base. So in this case, water it's behaving like an acid, but once it donates that proton, you produce your conjugate base. All right, the complementary acid, no, so this is base. I don't know why they're messed up. When a Bronsted-Lowry acid donates a proton. Oh wait, yes, donates a proton or loses a proton. All right, so basically these definitions are correct right here. Right, base plus acid, you make a conjugate acid on your product side. Acid it gives up, it donates its proton, you make a base on its conjugate base on the product side. So conjugate acid-base pairs always differ by one hydrogen, or one proton. You're either gaining or losing just one hydrogen. So question, are H2SO4 and SO42- a conjugate acid-base pair of one another? Are these conjugate acid-base pairs? No, because they differ by two protons. So what would the conjugate base be of H2SO4? The conjugate base of H2SO4. H2SO4 is an acid, right? HSO4, yes. Technically, this is H2SO4 is a strong acid, so there wouldn't be a conjugate base, but that's okay. What about SO4 2-? Is there a conjugate base here? Can we make a conjugate base? So a conjugate base, we lose a hydrogen, we lose a proton. For SO4 2-, are there any more hydrogens to lose? No. So SO4 2- only has a conjugate acid. So it can gain hydrogens instead, all right? And so its conjugate acid here would be HSO4-. And so we see that they are similar, all right? So what's interesting is that HSO4-, this substance, it has both a conjugate base and a conjugate acid. It can gain another proton, or it can lose another proton. And we call that an amphiolite, when it can do both. It can be both an acid or a base. Water also has that type of phenomena there. All right, so there's conjugate acids and bases. You should be able to recognize that. My motion detector went off. All right, so the big thing here, and I hope it looks familiar, is this equilibrium arrow. We can write K expressions for these things, all right? These reactions. So this reaction is describing ammonia behaving like a base, that it is grabbing, okay? It's grabbing a proton off of water in this case, making NH4+ and OH-. So let's write the equilibrium expression for this reaction. So remember what K is. It's generally products over reactants. So what's in our numerator? Concentration of NH4+ times OH-. What goes on the bottom? NH3. Does water go in it? No. Why does water not go in it? It's a liquid. Very good. Okay, perfect. So this is our KC reaction. Really, this is a KB expression where the B subscript just tells you that this reaction is describing NH3 behaving like a base, but it's still made the same way. So I'll just tell you right now that this is a KB expression. Okay, so based upon this information, I give you Kc, right? I give you the number. So 1.8 times 10 to the negative 5. Is that a big number or a small number? It's a small number. So at this temperature, do you expect more NH3 or NH4 to be present at equilibrium? NH3 is more present, yes, because K is small. Do you see how this is all the same? Same stuff, same stuff. So NH3 is more present when you have just like a beaker of ammonia sitting there. And you have some NH4 present. Okay. What is the Kc for this expression? What is it? NH3 over NH4 plus times OH. Cool. So that's the expression. How are these reactions related to one another? The reverses of one another. So what do you actually think the K value is for this reaction? Can we get the value for it? Yes, if we just take this value and how do we manipulate it if we reverse a reaction? To the -1, yeah, so 1.8 times 10 to the -5, and then we just take it to the -1 because we reversed it. I don't know what that answer is. 1.8 e -5 to the -1. 5.6 times 10 to the 2, 3, 4. Okay, so hopefully that you see that that's consistent. We already decided that NH3 is more present at equilibrium. And even when we reversed it here and got a new K, we see that now K is a really big number, but that's still consistent with the new reaction, right? That K being a big number, products are more present at equilibrium. NH3 is present because now NH3 is on the product side. All right, so same stuff. All right, let's kind of look at what all we will be talking about this term, so or this chapter. Do ensure that you're recognizing whether something is strong or weak. A strong substance is a strong electrolyte, so we use a like full-blown arrow, versus weak substances are chemical equilibria, they use this double arrow. So these substances at the top, these are our strongest acids. So what this graph is that it's you know, strong, and then we're like decreasing acid strength as we go down this graph or this chart. So what we see at the top, we have a lot of our strong acids that we've already identified, just some of them, not all of them. But as we go down this chart, we see how these are ordered. The acids get weaker and weaker and weaker. So these middle ones are weak acids. So they only partially dissociate their acidic hydrogens here. Only some of them pop off. Okay, versus strong acids, you think, you know, HA, big arrow, H+, A-. Only these ions are in solution. Versus weak acids, and I'm just generalizing it here, all 3 of these substances will exist in your solution. So do you remember from 1210 when we asked about like electrolyte character and like electrical conductivity? If you have a 1 molarity solution of HCl versus acetic acid, HCl versus acetic acid, which one conducts more electricity through the same concentration? HCl. HCl, because you get twice as much, you get a cation and anion for every mole of, you know, HCl you dissolve. But for a weak acid, you only partially get them. That you still have some neutral molecules that are reducing your conductivity. That's the whole idea of weak acids, that you have both kind of on the same side here. And then finally, down here, these acids are so weak that basically it'll never give up a proton. Okay, it's just so weak it'll never happen. But they're included here, and it's important because what we see on the base side is complementary. Okay. All right, so now adding the idea of bases. So you see how this is the same graph. It's the same table, all right? Oops, sorry. So on the red here, we have the acids. On this side, we have their conjugate base. So let me show you through, put you through this. Okay, so when HCl dissociates, if you ask yourself, what is the conjugate base of HCl? You would say Cl-. It loses its proton. So the thing is, when you dissociate a strong acid, you don't get a base at all. You get a salt. You get salt. That's it. Something that's very unreactive. It's already really, really stable. But the thing is, and where the detail is, and what we're going to study the heck out of, is when you take a weak acid and it donates its proton and makes its conjugate base, that conjugate base is also a base. Does that make sense? So here, let's look at this. Let's look at HF. HF is a weak acid. When that hydrogen gets donated to something else, I don't know, to a base, we're left with F-. That's the conjugate base, right? That F- can also behave like a base. And it can gain an 8 hydrogen back. All right, I like to think of it is that like weak acids and bases aren't very good at anything. It's like just average at doing two different things versus like a strong acid, super good at giving away freely its H pluses, but it's not good at accepting it back. Versus weak acids, they're just kind of good at giving away hydrogens or protons, and they're kind of good at accepting them again. Does that make sense? It's like you're so good at one thing that you can't do anything else. That's what a strong acid is. All right, versus weak acids and bases, they're like a jack of all trades. All right, so the idea here is when the strong acid donates a proton, what you get out of it, its conjugate base is nothing. It's just a salt, like a salt. Okay, like chloride, nitrate. It's just a salt. Versus we go so down in our acid strength that none of these substances are acidic, but once they lose a proton, they become super basic, super basic. So here, like OH, if it loses that hydrogen, like OH minus is pretty stable already. It's not acidic at all, but if we go onto this side, OH2 minus is going to grab a proton really quickly within there. So here are our strongest bases. Here are our strongest acids. All right, so that's how we read that chart. So the idea here is, yeah, stronger the acid, the weaker the basicity of its conjugate base. So if you have a really, really, really strong acid, its conjugate base is going to be super weak. Versus if you have a really, really weak acid, its conjugate base, once you rip off that proton and donate it somewhere else, that conjugate base is going to be really strong, meaning it's going to be really basic. Okay, that's the idea. All right, so let's think about water. Okay, water, and I kind of mentioned it before, we looked at ammonia. Ammonia, NH3, has that lone pair of electrons. Okay, and it can grab that proton right there. All right, and so we see where that proton is going. So in this case, you can see water is actually behaving like an acid, right? It's donating, it's giving away its H plus to ammonia. Do you see that? So water is behaving like an acid here. Versus, so, and we already know, ammonia is a base for the most part. Let's look at HCl. Well, if HCl is, you put HCl in water, I already know it's an acid, but if we kind of look at where the movement of things are, there's, two lone pairs on water, it's going to grab that proton off of HCl and form a new bond right there to make hydronium. That's our acid form in water. So we see here, water is acting like a base because it's accepting a hydrogen or a proton from our acid source. So we see that? So water can behave like an acid or a base. It depends on what the other thing is. Basically, it depends on what is the acid strength or base strength of water versus the thing that you're putting into it. That's what determines whether H2O will act like an acid or a base. So based upon this description, what theory would best describe this phenomenon? What do you think? Which one do you think? Do you think the Arrhenius theory can describe this? No, the Arrhenius definition does not. It just calls acids things with H plus, bases are things with OH, basically. It doesn't talk about movement, accepting of electrons or protons. So I don't really know what the correct answer is here. I would say B or C. Depends on how you want to think of it. Probably B, because we're talking about protons here, but definitely not A. That's what I wanted you to get. That in order to really recognize this phenomena of water, we need to know, okay, how's the proton moving within here, or where electrons are moving, if you want to think about it in a Lewis acid-base theory realm. All right, so based upon this idea that water can either we can lose a proton and make OH, that's what you see here, or can gain a proton and make H3O plus. That is actually something that happens in a pure sample of water. All right, water is not a great acid, it's not a great base. It actually can do both. It can either donate its proton or accept another proton. And the cool thing about water is it can do it with itself. So in the previous slide, I showed you water acting as a base and an acid on two different substances. Well, what if I have two water molecules and they act as acids and bases with one another? Here, I'll show you. Look at this picture. Okay, look at this picture. We have two water molecules. You see that? See the two? So here's their like structures. What if I took this lone pair on the one water and grabbed that hydrogen, making a new bond right here? In this case, this water molecule, the first one, is our acid because it's donating that hydrogen, versus the second water is the base because it's accepting that hydrogen. So do you see here how water, I'm showing you water is both acting as an acid and a base. This is called the autoionization of water. This process happens where we have two water molecules. A proton gets transferred between them. This is an equilibrium arrow. You get an H3O plus and a OH minus there. All right. This happens in water. It has its own K expression. So just based upon this equation, oh, I already have it. Based upon this equation, or balanced chemical formula, can't we get the K expression for this? H3O plus times OH minus, that's what this is. Do we see that? Okay. We give this a special K, so it's not Kc, we call it Kw. W stands for water. It's the K expression for water, okay? And this is a very important value in our world because we are water-based beings and there's water everywhere. So this number comes back to us. But also remember, H3O plus, chemists are lazy. So we know H3O plus exists, and that's how acid exists in water. But because we're lazy, remember, H3O plus is the same thing as H plus, right? So oftentimes you will see Kw written this way, H plus times OH minus concentration, okay? So these mean the same thing. They mean the same thing. I'm just pointing this out because I will probably write it this way because I'm lazy. All right, so this number, Kw, is really special because it has a known constant at certain temperatures. So at 25 degrees Celsius, which we will just call room temperature. And for the most part, 98% of the questions that I give you in this chapter, we're going to assume is at 25 degrees Celsius. I have to tell you otherwise if it's not. All right, Kw equals 1 times 10 to the negative 14. Okay, so I would say 98% of the time, this is what Kw is. It has to be a very specific question where I don't want you to use that Kw. For the most part, we are pretending we are operating at 25 degrees Celsius, which people call room temperature, but I think that's pretty warm. That's pretty warm. All right. Okay. So Kw will be really important for exothermic reactions. So let's kind of just review. K. Do you think this Kc that we just calculated is sensitive to temperature? Is this K any different than the K in chapter 15? No, it's not. So is K, big K, sensitive to temperature? Remember, K, big K, equals the rate constant forward over the rate constant reverse. K's, those little k's, rate constants, are those temperature sensitive? The speed at which a reaction happens? Yes, yeah. That's temperature sensitive. What equation do we use to estimate like how much K rate constant changes, the little k? Do you remember what equation? That dude Arrhenius, he came back, Arrhenius. The Arrhenius equation, okay, where we have K equals A, our frequency factor, E to the negative EA over RT. Yeah, so it's all coming back to that. So yes, as we change temperature, we change rates, we change Ks. All right. So what's the answer? Do you think yes? So that's the answer. So the answer is yes. So at higher temperatures, temperatures higher than 24 degree or 25 degrees Celsius, do you think more liquid water will be formed or more OH, H3O plus will be formed? So I'm just asking you, okay, if we raise the temperature, which way does the reaction shift? To the, what piece of information did I not kind of, it's on the slide, I just didn't say it. This is an endothermic reaction, all right? I didn't say it, but it's there. So that means triangle is on what side of our reaction? The reactants, right there. So you have to put energy into this reaction to go forward. So the fake way we predict which way a reaction goes when we add heat is we just treat triangle heat as a reactant. We know it's a reactant because it's endothermic. So if we add more reactant, which way does the reaction go? The product. So which one is formed at higher temperatures? The OH. Okay, good. So that was just Le Chatelier. But now, does kW, does that number, 1 times 10 to the negative 14, does it go up or down as temperature goes up? This is straight up chapter 15. Up. It's a 50-50 guess, right? But let's think about it. Again, the piece of information that I didn't really mention here or put too much effort in here is the endothermic part. So if we drew the reaction coordinate, it would look like this, right? So this is the forward. This is the reverse. So the idea here is that because this is an endothermic reaction, the products are at a higher energy. There's a difference in activation energy whether you're going this way, whether you're going forward, or whether you're going reverse. All right, so there's an activation energy there and activation energy there. So if we raise the temperature, okay, so then based upon this diagram and the activation energies, which reaction is slower, has a smaller rate constant, the forward reaction or the reverse reaction? Yeah, the slower reaction is the one with the bigger hill, the bigger energy jump, right? Like it takes you longer to walk up that hill. So if we heat up the reaction, we give the reaction more energy, which direction, forward or reverse, is more sensitive to that extra energy that's being given, that extra kinetic energy? The forward, the one that's already slow. The one that's already slow. So this idea, this last question, K equals Kf over Kr. When we increase temperature, the numerator increases more. Increases more. Do we see that? So that means K is actually going to go up. It's going to increase as temperature goes up. And you can see that. You can look at kWs for water at different temperatures, and you see that the number gets a little bit higher. Also, that idea kW gets bigger is consistent with our Le Chatelier prediction, because if kW gets bigger, what substance is formed more at equilibrium at higher temperatures? If K is larger, products or reactants? If that number is getting bigger, the numerator is getting bigger, so you make more products, and that's consistent with what we said in the previous statement. See how all of it's tied together? All of it's tied together. Okay. All right, so let me just do these 2 slides and then we'll do review. All right, self-dissociation of water is an equilibrium. So here I give you 2 different K values, KWs. So here's KW at 25 degrees, and yes, we predicted correctly. Here's at 50 degrees, it's a little bit higher at 50 degrees at a higher temperature. So let's calculate the pH of water. This is the same exact ice table that we've done before. I want to know what is the H plus concentration at equilibrium for a pure sample of water. So let's do 25 first, okay? If I have pure water, right? Some amount, doesn't matter. I'm just going to put N. And I have 0 of this stuff. If this is an equilibrium process, for every 2x amount of water I lose, how much H3O plus do I gain? Plus X. How much OH do I gain? Plus X. So then if I add everything up, it's N minus 2X, X, X. But the great thing is, is when we write our KW expression and do products over reactants, do we put all this stuff, all of it in our expression? No, we don't include what piece of information? Yeah, we don't have to include that. So it didn't actually matter that I put N there. We're only putting these two values into our KW expression. All right, so we get that KW equals H plus times OH minus. And so we get that that is equal to X squared equals that KW value for this temperature. So 1 times 10 to the something. 1 times 10 to the negative 14. And so we get that X is equal to 1 times 10 to the negative 7 molarity. So that is the concentration of H plus and OH at equilibrium. You see that? That's the same stuff as the previous chapter. It's just a nice table. And it's actually a fairly simple one at that. All right, so these concentrations I just got, I'm just going to peek to the next slide. We can take that concentration and get the pH. So this is typically what you see, like that concentration of H plus is really small. You see it's really small. Like 1 times 10 to the negative 7, there's like 6 freaking zeros in that. See, chemists are lazy, all right? And we don't like to write scientific notation. So we came up with another scale. It's called the this pH scale. That means pH is equal to negative log of that concentration we just got. And in doing that, what we get is that the pH of this solution is 7.0 pH. All right. If you put this number into negative log of that number, that you get the pH, that's what it is. And so I don't know about you, but writing 7.0 versus 1.0 times 10 to the negative 7 molarity is a lot easier just to write 7.0. Actually, it should be 7.00. Sorry. Do you see that? All right. So pH is equal to 7. We can also calculate POH here. It is also 7. POH is also 7 because it has this, I wrote 0. We have the same concentration of OH, so 7.00. All right, let's do the same thing but at 50 degrees. Will the ice table look any different? No, it's going to look the exact same. The only difference is the KW value we use. So for every 2x amount of water we lose, we gain x amounts of both of those things. So n minus 2x, again, this number doesn't actually matter because it doesn't go into kW. And so it should look exactly the same. So kW is equal to x squared, but instead of equal to 1 times 10 to the 25, we get 5.5 times 10 to the negative 14. And so what we get is that x equals 2.346 times 10 to the negative 7. This is equal to our H plus concentration at equilibrium and to our OH concentration at equilibrium. Okay, so based upon this, but this is at 50 degrees. Note that this is at 50 degrees. We have a different KW value. Can someone calculate the pH of this water at 50 degrees Celsius? So you're putting this number, so negative log of 2.346 times 10 to the negative 7. What is that? 6.63, that's fine. Yeah, pH. Okay. So the whole idea, okay, you get through your mind right now, that people say neutral means pH 7. That's wrong. That's only true at 25 degrees Celsius. We just proved it. At 25 degrees Celsius, when KW equals 1 times 10 to the negative 14, you take the square root, you get that both the concentration of H plus and OH is 1 times 10 to the negative 7, 7 pH, 7 POH. So the real definition of a neutral sample is when H plus concentration equals OH concentration. That's the real definition. All right, so in this sample at 50 degrees Celsius, right off the bat, you might be like, oh, hot water is acidic? No, it's not. It's not, it's still neutral. Because neutral means when these two concentrations, H plus and OH, are equal to each other. Are they equal to each other? Yes, we just took the square root, they're both the same number. It is neutral. It's just that that neutral pH is not pH 7, what we are accustomed to. It's actually a different number. And it's because Kw is a different value at higher temperatures, lower temperatures away from 25. And specifically why it looks like it got more acidic is because this is an overall endothermic reaction. As temperature increases, the K value increases as well. Did you all think that pH 7 means neutral? Yeah, I think most of us do, but in reality, that will get you most of the way there. So what's interesting is, like, you know, our bodies don't operate at 25 degrees Celsius. I don't know what physiological like temperature is, like 37. I'm just making up numbers. So the water that's in our body, they're following an equilibria that's not pH 7 equals is neutral. It's something else because our bodies are at 37 degrees Celsius. That might be super wrong. I'm not sure. Again, I don't like living things. Yeah, so I think that's interesting that the equilibria in our bodies are a little bit off than what our intuition says. Okay, let me just quickly talk about how we calculate pH, POH. Understand that P, anything, just means negative log base 10. This is log base 10. I know we just came from natural logs a little bit ago. This is log base 10. It's negative log of anything, the concentration of anything. So pH is negative log the concentration of H. POH is negative log the concentration of OH. P bananas is the negative log of the concentration of bananas. Okay, P means anything, like negative log of anything, because we'll look at things like pKa, pKb. Those are the negative log of Ka, or the negative log of Kb. P is just like a function, I guess. All right, okay. So that's how we go from a concentration to a pH. We can reverse it, all right, where we can go from a pH and go back to a concentration. So how to undo it, just to put it in a slide, is 10 to the negative pH. That's how you convert it back to H+. Versus, what is the concentration of OH when you're given POH? What would that be to undo it? It would be 10 to the negative POH. Right? So those are related. Okay, so the idea here, if you've ever worked with pH before, oftentimes we say, oh, pH plus POH equals 14. That 14, I hope you recognize, comes from Kw, right? Kw is 1 times 10 to the negative 14, okay? This relationship is only true at 25 degrees Celsius, okay? But again, 98% of the time we will be working at 25 degrees Celsius. Okay, so let's do some conversions. Okay, H to pH. What's your pH? So I'm putting negative log 1.5 times 10 to the negative 5 into my calculator. So negative log 1.5 E negative 5. 4.82398. Okay, so on the next slide, I talk about rules with significant figures when it comes to logarithms. But I'm going to describe it right here. How many sig figs does our concentration have? 2. Okay, so I'm going to straight up tell you, when you take a log of something, this number, I don't want to say, see, I made a mistake before. I said it doesn't have sig figs. We ignore the sig figs in that 4. The reason is that 4 just tells us how big or how small that number is. That 4 is related to the negative 5. That's right here. It's the exponent. It's telling you how big or small the number is. So when you write a pH, you want to make sure that you have enough decimal places that reflect the number of sig figs in your in the molarity that you're given. So to the correct number of sig figs here, this would be 4.82. I'll show it in the next slide. All right, what would the POH be? How would you do this? Assuming 25 degrees Celsius, how would you get your POH? 14 minus 4.82. You can get that, or you can use the KW expression where KW equals H plus times OH minus. You can do that too. You know H plus, you know KW, get OH minus, get POH. But if you just do the subtraction, you get 9.18, right? I think that's it. So that's POH. All right, let's do pH to H plus. All right, so if you're given a pH and you want to get to H plus concentration, you do 10 to the negative pH. So this is 10 to the negative 11.51. So 10 to the negative 11.51 equals a tiny number, 3.090 times 10 to the negative 12 molarity. And so how I go about this is I see in the pH number, any integer doesn't contribute to our sig figs. So my pH value only has 2 decimal places. So I want to round my molarity to 2 sig figs. So 3.1 times 10 to the negative 12 molarity. All right. Now we want to get OH concentration. So there's a couple ways you can do this. You can convert pH to POH and then just do the 10 to the negative POH. You can do that. Or you can take this number we just got and use the KW expression. All right, H plus, OH minus. All right, we know this, we know that. Just solve for OH minus. I'll do this one. I'll do the first one. So POH here, 14 minus 11.51 is POH equals 2.49. So that means our OH concentration is equal to 10 to the negative 2.49, whatever that is. 10 to the negative 2.49 equals 3.2 times 10 to the negative 3 molarity OH minus concentration. All right, so again, there's a couple ways we can talk about concentration of acidic basic things. You know, instead of just giving you straight up a concentration of H plus, instead I might give it to you in pH instead. But recognize that pH value is related to a certain concentration. So let me just talk about significant figures with logarithms, and I'll prove it to you how this all works out. Oh, and just mention kind of, if you didn't know, when working at 25 degrees Celsius, we will say pH neutral is 7 because that's when H plus equals OH concentration. When there's too much H plus, when there's more H plus present, that's an acidic solution. When there's much more OH minus present, then that's a basic solution. So our first example here, is this acidic or basic? This first one? Do we know if it's acidic or basic? It's acidic. A couple reasons. You can say, oh, the pH is less than 7. Okay, if the pH is less than 7, then that's an acidic solution. If it's greater than 7, then it's basic. So this second one, acidic or basic? 11.51, that's basic. Yeah, and so if we compare these concentrations that we got, see we got H plus, we got OH minus, which there's much, much, much more OH minus present. It's only to the negative 3 versus H plus is to the negative 12, right? And so again, that's saying it's basic. All right, let me just show you those significant figures and logarithm rules. Okay, so a logarithm, see, I don't teach math. A logarithm, if you do like log 100, if you put that into your calculator, log 100, you get the answer 2, right? Agree? You did it? You got 2. What that means, where that 2 comes from, is because base 10, log is base 10, it's because 10 to the 2 exponent equals 100. That's why the answer is 2. I don't know a better way to explain it. Right? So if we had log 1,000, 1000, the answer would be 3. So you see how it's essentially counting the place values or the number of times you have to multiply by 10. So that 2 is basically telling you like how big that number is. If we wrote the number 100 in scientific notation, wouldn't we write 1 times 10 to the 2? In Gen Chem, if I asked you how many sig figs does that number have, what would you say? What would you say? 1 times 10 to the 2. 1, yes. All of the significant figure data is where? In what part of that scientific notation? It's just in the first number, like right here. Like if I put 1.0, that would have 2 sig figs. But didn't we warn you that this 2 has no significant figure data in it? It actually has infinite sig figs. Because when you write this number, like how do you get there? You take the decimal place, you count how many times you have to move it. That's what that 2 means. So is that 2 a measured number or an exact number? It's exact because we counted it. Like, would you bet $1 million that you move that decimal place 2 times? I hope you would say yes and get $1 million. So that is an exact number. So what I'm saying is that 2 has infinite sig figs. So it's the same thing with logarithms. When I say log 100 to 1 sig fig is 2, that 2 is just indicating the exponent. So it actually has no significant figure data in it. So really, if we wanted to express log 100 to the correct number of significant figures, it would be 2.0, not just 2, it's 2.0. All right, so what I mean here, what you're looking at is the number you're taking, like this would be concentration, right? This has 1 sig fig, so you want to make sure your answer has 1 decimal place. That's basically it. And the reverse. If you're given a pH, look at how many decimal places it is. Recognize that that integer number just tells you how big or small the number is, so there's no significant figure data there. And make sure that your answer has that many sig figs of the number of decimal places you have. So without actually doing the math, log of this number, how would we write it? Okay, just put it in your calculator then. I'll just put it in my calculator. Do I have it? No, I don't. Okay, negative log 0.00345. So I'm going to just write the whole number, 2.46218. How many sig figs are inside that logarithm, in that concentration? 3. So does that mean I want my answer to have 3 sig figs? No, the 2 doesn't count. So when I report my pH, it needs to have 3 decimal places instead. The 2 doesn't count. So the answer is 2.462. 3 decimal places. Following along? All right, the next one. So how many sig figs in the concentration? 2. So then how many decimal places will my answer have? 2. So if you put that into your calculator, negative log 0.12341, I get 11. Wait, is that right? No, I did natural log. 12341. I get 4.9208. So since this has 2 sig figs in the number, I need 2 decimal places in my pH. So this pH is 4.92. All right. Okay, let's go the other way. Let's go the other way. So this pH is 5.626. If I want H plus concentration, how many sig figs will my molarity have? 4? 4 sig figs? 3 sig figs, yes, because the pH value here, there's only 3 sig figs within there. It's the decimal places. So yeah, our answer is going to have 3 sig figs, not 4. It's going to have 3, whatever that answer is. Okay, this one. How many sig figs will my molarity have if I give you this pH? 1, because there's 1 decimal place. This is tricky, all right? And it's also the same rule for natural log, but I skipped over that when we talked about rates, because the numbers weren't really important, but the numbers are important here. Okay, all right, so that's it. Let's do midterm practice. What chapter do we want to do? Is there any question someone has like a burning desire that I do right now? Oh, well, first, before we do that, let me just like remind you where to find this packet. It's on Carmen, right? Teacher, go to our class. It's under modules. Under modules, under the lecture module, there is a midterm resources module, and you'll find it there. Okay, modules. Do we all find it? We find it? Okay. Yeah, under lecture resources, there's midterm exam resources and then recitation. Okay, it's right there in that page. Okay, so is there a certain question we want to do? Is there a certain chapter we want to do? 13, solution chemistry, kinetics or equilibrium. We already did all of equilibrium, but I can do some more if. 13? Anyone want to say a number? Or you just want me to start working? Just start working? Okay, just shut up and just do stuff. Okay. I like this one. Let's do number 3. Okay. In which case would delta H solution be expected to be negative? What the heck is delta H solution? So my strategy here is relate this to a topic we talked about. Is there some type of equation we use, some type of like concept we talked about that incorporated delta H solution, delta H solute, delta H solvent? Yeah, it's that graph, that funny graph we talked about, where all of this is hypothetical, where there's a certain amount of energy to break your solute. There's a certain amount of energy to break your solvent, so that could be like water or something. Once you break up your solute and solvent, basically, if you add those two, things up, you get an attraction where you bring your solute and solvent together, forming those new IMFs that I mentioned up here, right here, right? That we can talk about forces in your solute, forces in your solvent, but you might have new forces when you combine your solute and solvent. And so that arrow, do we know what that big downward arrow is called? Delta H of mixing, yes. And so where our delta H of solution comes into play is the difference of where did we start and where did we end up, all right? And so it's this difference. So it's asking when is delta H solution to be negative? So how I've drawn it right now, is this a negative delta H solution or a positive? This is negative, yeah, because we ended up more stable than we started. So this is a exothermic reaction. This is a negative delta H of solution. So when you dissolve this solvent or that solute in water, would you expect the water temperature to go up or down? If you dissolve it and you feel it. Does it feel warm or does it feel cold? It should feel warm, all right? Versus, so this is what the question is asking, but if we had a delta H of solution that was positive, it's the same idea here where we have energy to break pure solute, pure solvent, and then our delta H of mixing is here. In this case, delta H of solution is a positive number. This is an endothermic dissolution process. So in an endothermic process, when you mix the salt, it will feel cold. So those are how cold packs work, okay? So this is kind of funny. These questions are like this type of reaction where we have an endothermic reaction. They're not super energetically favorable, like thermodynamically, if we just think about it from an enthalpy standpoint. We're making weaker bonds. That's what this is saying. We're making weaker bonds in the mixture. The reason they happen at all is because of entropy. Remember, like I mentioned that any like positive delta H value type of reaction that does happen spontaneously is because of entropy. And so yeah, a positive delta H solution is driven by entropy. Anyway, okay, because this reaction, the one where it's exothermic and a negative delta H solution, this is driven by enthalpy, meaning that we're making stronger bonds in our products. Okay, let's actually answer the question. All right, so when would delta H solution be negative? So we are asking, we have a bunch of different interaction. So even without looking at the answers, when is this negative? When this arrow is big or small? Big and negative. Versus, because if we look at this arrow, sorry, I have it kind of shown a little bit differently here. I should put them on top of one another like that. Here, delta H of mixing is smaller than the delta H's of the energy to break the solute and the solvent, like the pure substances. So here, you have an endothermic process. So yeah, so then which is the right answer? Is it C? Yeah, and be careful how it's like being worded. If we go through all of these, solute-solute interaction, that is describing delta H of solute. Solvent-solvent interaction is describing what? Delta H of solvent. But solute-solvent is describing what delta H value? Mixing, yes, delta H of mixing. So we are looking for the one where mixing is greater than the sum of those two. So I think, is it C? Yeah, solute-solvent interactions are much greater. Yes, okay, very good. All right. And kind of putting it together, there's an equation we can, oh, I think that's the next one. Yeah, let's just do the equation. All right, everyone loves math. Just plug and chug. So basically, if you know this cycle, like recognize conceptually what it is, you can also get your equation here, where the delta H of your solution, so whether a reaction, what we feel, exo or endothermic, is equal to delta H of the solute plus delta H of the solvent plus delta H of mixing. But do recognize that delta H of mixing is usually a negative number. Actually, it's always a negative number because it's attractions. So just know that. And so now it's just plug and chug. But do you see how I don't give you this equation on the exam, but do know that we can get this equation from inspecting this graph that we just came up with. And you kind of have to know this graph, conceptually to answer these questions. And so I think you just plug in the numbers. What are we calculating? Delta H solution. Look, that's solute. Yeah, so that number solute. Solvent is 220. Look, and delta H is a negative number. Plug it in, and I think the answer is something. I don't know. What is it? Negative 40. All right. So would this beaker get hot or cold? Hot, yes. Very good. Yay. What is stronger? The bonds in the pure solute and solvent, or the bonds, attractions in the solution? Solution, yes, the bonds are stronger in the solution. Yes, because it's an exothermic reaction. The system's losing energy, and your substances are getting more stable. Okay, let's do 5. Everyone hates 5. Everyone hates beakers. Okay. So the solubility of salts at some temperature is 35 grams of sodium chloride in 100 grams of water. So based upon that solubility, so 35 grams of NaCl in 100 grams of water, if I have 100 grams of water, what's the maximum amount of salt I can dissolve? 35. If I have 200 grams of water, what's the maximum amount of salt I can dissolve? 70, yes. So recognize that solubility is, what kind of property is it? Intensive? Is it intensive? Based upon the temperature of your sample. But the actual amount of solid I can dissolve is extensive. It depends on how much solvent I have. Does that make sense? Okay, good. All right, so based upon this information, beaker 1 contains 30 grams of sodium chloride. Beaker 2 contains 50 grams of sodium chloride. How can we categorize those beakers? Beaker A, what would we call that? Where is all the salt? Think about in your brain, where is the salt? Is it sunk to the bottom, or is it dispersed evenly to make a nice saltwater solution? Wait, beaker 1 is unsaturated. What's the definition of unsaturated? It's a solution that can accept more solid. If I only have 30 grams in 100 grams of water, if I gave you an extra gram of NaCl, would it go into solution? Heck yes. How about another gram? Yes, until it gets to 35. Yes, so beaker 1 is unsaturated, right? You can think it can still accept like 5 more grams of salt. Okay, beaker 2, what does beaker 2 look like? It's saturated, but what does it look like? But how much solid at the bottom? 15. Where did we get that? Yeah, we subtracted. We already said the maximum that 100 grams of water can hold is 35. So once I get to like 36 grams, it's just going to fall to the bottom. So what this would look like, it's saturated. What it would look like is we would have, 100 grams of water. We had 15 grams of solid on like at the bottom, but if we actually took the concentration of like the liquid, that would be a concentration of 30 grams per 100 grams of water. It would have the same like that max solubility dictated, by what I gave you before. Okay, we already answered these. Which beaker can accept more NaCl? 1. Which is saturated? 2. Okay. Calculate the concentration of NaCl in each beaker in molality. Yay. Okay, molality. What unit is that? Moles over kilograms of solute. Yeah, molality. I didn't misspell molarity. No, I mean molality. All right. So based upon this, moles of what exactly? Salt, NaCl. Okay, good. All right. So looking at this, beaker 1 contains 30 grams in 100 grams of water. So I, right off the bat, know what my denominator is. Do you see that? It's 0.100 kilograms. I just need to figure out, okay, how many moles of sodium chloride do I have? So this is beaker 1. Yes. Yes, it is, because we only have, yes. I don't know what my mouth said, but my hand was wrong this time. Yes, it's solvent. It's moles of solute over kilograms of solvent. So in this case, since we have 100 grams of water, which is the solvent, we already know what the denominator is. It's 0.1 kilograms. So the difference is here, we just have to do a quick calculation to get moles of sodium chloride. I know that there's 30 grams in there, and so hopefully this is, just a quick molar mass conversion here from 1210. There we go, grams, 1 mole. I don't know what my answer is. I don't even know what my key is. Okay, I think the answer for beaker 1 is there's 0.513 moles of NaCl over 0.10 kilograms of water. Ignore my sig figs. This is 5.1 little m NaCl. That is beaker 1. That's beaker 1. Let's do beaker 2. So the idea here is in beaker 1, all 30 grams of salt are floating in the water. There's nothing at the bottom. But what's different with beaker 2 is that not all 50 grams of salt is dissolved in the water. We already described what beaker 2 looks like. It looks like 35 grams dissolved, 15 on the bottom. So when we calculate molality for beaker 2, what number do we use to get moles of NaCl dissolved? Do we use 50? Do we use 15? Do we use 35? What number do we use? 35. We use the number of NaCl, like the grams actually dissolved in the water. So to do beaker number 2, we do the same thing, but 35 grams of NaCl, 58.44 grams, 1 mole. All right, that gives you some mole amount, I don't know, 0.598 moles. Oh, I have some mistakes in here. Who knew? It's just a unit thing, okay? And then so there we go, that's molality, and I think it's 6.0 molality. NaCl is in beaker 2. So the idea here, probably the most common mistake for determining the molality of a saturated solution is students will use the 50 number. Because they're like, oh, you put 50 in there. Yeah, there's 50 in solution. No, you told me that there's 15 grams sitting at the bottom. That's not in solution. So we already said the maximum that this water can hold is 35 grams. That's the stuff that's in solution. There, yes. Beaker 1. We'll accept more, meaning that I think you might be misunderstanding the question. If I have a big glass of water and I put a tiny bit of salt in it, all right, if I took another pinch of salt and put it in it, would it dissolve? Would that second pinch dissolve? Yes, it can accept more salt. What if I added like another little pinch? Yes, it will keep accepting salt until it reaches the max solubility determined by that first sentence in the question. So that we're under the solubility line. Does that make sense? I think you're just misunderstanding the question. That's the maximum, but did it reach there? It's at the beaker 1? Yes, beaker 2 exceeded it. So once it gets to 35, all that extra solid you put in just sinks to the bottom. It's not going to go in. Yeah, you've already filled your bucket, I guess, is a way to think of it. Okay. All right, let's think about these changes for the beakers. Oh wait, let me pretend. What if I added to beaker 2? What if I added 10 more grams of salt? Would the molality of the solution change? Okay. How about what if I added? Let's look back at the solubility here. What if I added 100 grams of salt to 200 grams of water? What would the concentration of the solution be in molality? You should be able to do this in your head. Not quite. And I think I tricked you previously. I was asking, what is the, so I'm saying we have 100 grams of NaCl, 100 grams of NaCl, okay? And we have 200 grams of water. First, ask yourself, is that a saturated or unsaturated solution? Saturated. It is saturated. So yes, you are right. You're right that 200 grams of water will dissolve twice as much salt. How much salt is in solution? 70. But there's 200 grams of water. So what is the concentration of salt in the water? We already calculated it. It's 6 molality again. It's 6 again. Because it's saturated. All frickin' saturated solutions of NaCl are going to have that molality. All of them. Doesn't matter if it's a thimble. It doesn't matter if it's a frickin' ocean. If it's saturated, it's 6.0 molality. You can prove it to yourself. Just prove it to yourself. Like if you had 70 grams of salt in 200 grams of water, you'd still get the exact same number. Okay, all right. All right, other questions? Oh wait, no, we're gonna do these ones. Okay. So that 35 grams over 100 thing, that is only specific to that temperature. I don't know what temperature it is. Solubility of substances change based upon temperature of your sample. So cooling or heating your beakers will change this number. Yeah.
So if we have something that's asking for like gram over 100 grams, would we divide that value out when we give our answer, or do we just keep the over 100?
Wait, what?
Okay, so like for example, like our FPD lab, we had something where we had to have like we wrote it out as like 35 over 100. So I was just curious if we keep it like that, or do we do like 35 divided by 100 and then that's our answer? know if that makes
No, it does. It depends on, I'm assuming this is a smart worksheet thing. Is that what it is?
somewhat.
I don't
I'm
know.
just talking about in general, like when you're writing out the answer. Like,
If I was talking about solubility, that 100 part is part of the unit. So
divide it out.
no, because what you would be doing is you're saying, oh, that's how much salt will dissolve in 1 gram of stuff. So you want to actually keep that 100 there.
Okay.
But numerically, it'd be the same number. Like this is 0.35.
Okay.
That is the same. So this number is the same as saying 0.35 grams of sodium chloride will dissolve in 1 gram of water. But this is easier to kind of visualize. Yeah, 100 grams, I kind of know how much that is. Yeah, I don't, yeah. Do you have something to add? Yeah, per 100 grams is the unit, yeah. But I don't know how to put that in a smart worksheet. I don't even know what a smart worksheet is. Yeah. I think that was her question. I'm not quite sure. So for me personally, if I was trying to calculate the solubility of your salts, I would report it in a table as this, 35 over 100 grams. I would like work it out so I could report it that way because that's a number that is more meaningful to us as chemists instead of dividing it out and reporting 0.35. Like that might be fine for like compiling on Excel to like calculate things, but when I report it like as a final thing, I would do it this way. Does that make sense? Okay, all right, so let's do these things. All right, so cooling the beaker, heating the beaker, we actually change that solubility number, okay? So if we cool the beaker a little bit, is the solubility, the ability for water to dissolve salt, will it go up or down if we cool it? If we cool it. It's going to go down, yes. So let's pretend we cool the beaker and it goes down to 32 grams per 100 grams. Do the beakers change? Let's just say the solubility just goes down a little bit. Does beaker 1 change? No, because the max solubility is still above what's in it. But does beaker 2 change? Yes, what happens? 3 grams fall out. 3 grams have to fall out because the solution above that, that solid has to remain like whatever the solubility is. Okay, good, good, all right. But if you cooled it enough where the solubility was below 30 grams, then beaker 1 might start to crystallize, all right? I just said just cool it a little bit, okay. What if we heat the beaker? Our intuition says solubility goes up. Okay, so let's just make up a number. Let's say the solubility goes up to 40 grams per 100 grams. Okay, so if that's the new solubility, we didn't change the like stuff we put in the beakers. All we're doing is changing the solubility. Does beaker 1 change at all? No, we're still unsaturated. All we did was change the ability for that solution to maybe accept more salt if we wanted to. Does beaker 2 change? Yes, it dissolves more. So how much more? 5 more grams. 5 more grams will dissolve. All right, but beaker 1 will not change at all. It's still unsaturated before, it's unsaturated at this new temperature. Yeah.
More.
Yeah, more solid.
Does it become unsaturated?
It becomes unsaturated for a split second. Then it goes back up so it can become saturated again. It's actually an equilibrium. We're just like changing K kind of here. Yes, all right. What if we remove 5 milliliters of solution off the top? If we take beaker 1 and we just kind of splash some solution out. Does that change anything? No, it does not. Because it's like when we did dilutions and you just take a small portion of like a big stock container. Both those portions, when you split it up in 2, have the same concentration. You're just taking some of that substance out. You're not changing the solubility. You're not changing the concentration of anything. You don't change anything about any of the beakers in either just F. It doesn't change anything. Nothing. All right, question? Of what? Of what? A, of beaker 1? Beaker 2, does concentration go up? So we predicted in D that the solubility, the max amount that 100 grams of water can hold goes down. That it can only, we just made up a number, it says we can only hold 32 grams of salt. And so we said that some of that salt leaves the solution. So we're losing some of the moles of NaCl in this calculation. But are we changing the volume at all? No. So basically what we're doing when we cool the beaker is that this number goes up or down. This number right here in our molality calculation goes down. So does concentration go up or down? Down, because the solubility decreased. We're losing moles of solid and it's falling to the bottom. It's no longer in solution anymore. Does that make sense? Okay. But E, if we heat the beakers, beaker 2, if we calculate molality for beaker 2, if we heat the beaker, is the concentration going to go up or down? Up. But what about in beaker 1? Does the concentration change in beaker 1 if we heat it? No, because we don't change the number of moles of stuff. We're not changing the volume of anything. We're good. All right, so what about G? What if we add 5 milliliters of pure water to both beakers? What happens? We're adding water. But that's true. If we added solid, beaker 1 can accept more. But what if we add more water? Beaker 1, it's just like nothing, you just dilute it. You're literally just diluting it. That's it, diluting. But other than that, nothing really changes. You just dilute it. But beaker 2, I think some bigger changes happen. If you add more water, are we still talking about 35 over 100 grams? No, we're talking about 105 grams. So it's going to dissolve a little bit more solid within there. So you're going to lose some solid on the bottom, but does the concentration on the top change? No, it's going to still remain the same. I mean, when you add water, it's going to momentarily dilute, but then the system's going to dissolve more solid to bring it back up to that 35 over 100 ratio. So that's 1, 2, beaker 2 will dissolve more solid. Okay, what if we evaporate 5 milliliters of solvent off the beakers? So just a little bit, we just evaporate a little bit. Beaker 1, it's the same idea here than the previous question. Beaker 1 will just become more concentrated. I'm assuming we're not evaporating it so much that we change the concentration drastically, so we're above the solubility point. So I'm just saying that we evaporate a little bit off. So it's just going to get a little bit more concentrated, like a little bit more than 5.1. It might be like 5.2 or something. Concentration just goes up. Yeah? At equilibrium, yeah. Good question, yes. And then finally, beaker 2. If we evaporate 5 milliliters of solvent, what will happen for beaker 2, the saturated one? Some solid has to fall out in order to maintain that 35 to 100 gram ratio. There's not as much solvent, so some solid has to fall out. Okay, all right, there we go. These are tough things to visualize, I think. I think if everyone just goes home, takes a huge handful of salt and some water, go to the stove and just play around with it until you see things dissolve more or not. I don't know. Yeah. Okay, other questions? Is there one that we really want to do? 7. Yeah. Density. So, okay. Let's think, so when we were in Chem 1210, what was basically the only concentration unit we used? Molarity, yes, molarity. Big M, moles of solute over what? Liters of solution. That's the important thing. Okay, we learned about a lot of other units of concentration in this class. So this is how I categorize them in my head. We've talked about percent mass of stuff, right? Percent mass in a, or not mass, percent composition, you know, no, it's percent mass, that's what I want to say. Yeah, I could say like your sample is 50% by mass sodium chloride, 50% total mass, right? 50% of that mass is towards like your solute or something. What else do we talk about? We talk about molality. Oh, so maybe I should say mass solute over mass sample times 100. We talked about molality, which is moles of solute over kilograms of solvent. What else did we talk about? What other ones are in here? So there's percent mass, mole fraction. We did that one, mole fraction. So we'll just say of the solute. That is moles of your solute over total moles of your sample. Okay, so the reason I have a big line separating them is because all of these ones, percent mass, molality, solute, you are, when you calculate these values, you can calculate the mass of or moles of your solute and solvent separately. You can treat them separately and then add them up. They're additive. Okay, like I talk about mass of sample. Your mass of your total sample is your mass of your solute plus the mass of your solvent. The total moles of your sample is the moles of your solute plus the moles of your solvent. Those are all additive. The problem with molarity is that liters of solution is not necessarily liters of solute, liters of solvent, that it's not additive. So in order to go from these ones, all of these three, these three concentrations, you can jump from all of them, not easily, but you can jump between all of them and not need density of your sample to go from percent mass to molality to mole percent. You can jump between all of these conversions if you just use the right molar masses and all of that junk. What's different is if you want to go from any one of the ones on the left side to molarity, you need density of your sample. That's what in my brain, that's what works for me. I just know in order to go, or the other way, or if you wanted to go to molarity to the other side, you need density to make that relationship, okay? Because if you're doing questions like this and you are stuck, this is probably why. So in my mind, jumping between these ones are systematic, but like to make the hop over to molarity land, you need density, or the other way. All right, so let's do this one. So look, because we have the density of this molarity aqueous solution of blah has that density, what is the molality of the solution? So here we're going from molarity to molality, so we do need density, but I'll show you where we need it, all right? So my strategy here is I take the concentration unit that's given, right? And I write out an equality that helps me understand what it means. Molarity means 0.872 moles of potassium chromate, CrO7, equals what? 1 liter of solution. So I'm gonna make things easy for myself and just pretend I have 1 liter of solution. So let's remind ourselves also what molality is. It's moles of solute, so this is the potassium thing, over kilograms of solvent, so that's water. So if I start with liters of solution, 1 liter of solution, how many moles of solute do I have? 0.872, so I already have the numerator, yay. That's why I like to make it easy for myself. So I have that, that's gonna go in my numerator, but it's the bottom that I need to figure out now. So I'm gonna use this whole idea that I'm gonna just start with a liter of solution. I'm gonna use that density that's given, all right? So how do I do this? So liter of solution, so 1 liter, 1,000 milliliters, that's the same as a centimeter cubed. So 1 centimeter cubed is 1.129 grams. So when I put this into my calculator and I get 1129 grams, that's the mass of what? Of the solution, because I started with volume of solution. That's of my solution. The mass of your, the mass, so gram amount of your solution is the mass of your solute plus the mass of your solvent. We want mass of solvent, right? That's the molality, like the thing we got to put in our equation. The other piece of information, mass of solute, how can I get that? How can I get that? From the moles. Yeah, we already dictated how many moles of solute we have. So if I know how much, so the whole idea here is that I know that this is solute plus solvent. I want the solvent part. I can calculate the solute part from the 0.872 moles of K2Cr. Okay, that's a 4O4. All right. How do I get the mass of my solute? Molar mass, which I give you because I'm super nice. So 1 mole is right there, 194.19. So this many moles of that potassium chromate stuff is 169.3 grams. That's of my solute. So that means if we compare these two numbers, how much solvent do I have? It's just the difference. You see that? And that's the number that goes in the denominator. All right, so putting it all together, so that molality equation is 0.872 moles over 100 or 1029 minus 163 or 169.3, and that's divided by 1,000. I think that's the answer, whatever that is. I think the answer is D. Cool. These are, understand that molarity, it's that denominator has that solution part. Oh, I thought we were done at 2:30 or 12:30. Sorry. Yes. All right. So there we go. You have access to the key. Best of luck.